I hope it will not take the whole hour, maybe depends on how many questions you have. But yeah, I'm really interested to give this talk today since it's a really different perspective I have on the topic from my daily work. And yeah, it's not only about challenges, but also about success stories on the use of AutoML for domain experts in the context of renewable energies. And in short, about the purpose of this talk, I would just like to give you some inspiration why AutoML is needed from maybe in a different aspect than you might use it in your own work. And I will give you some insights why no-code and AutoML can be quite a game changer. And in the last part of my presentation, I will give you some additional use cases for machine learning in the context of renewable energies. Markus already showed some examples, but I have quite some different ones. So today you will get the whole package of renewable energy, machine learning problems, and how machine learning and AutoML can be used for that, and yeah, is already used. So, and also it's important to say what this talk will not be about. So I will not give you any deep dives into AutoML methods since I'm not an expert. This is also why I'm here to learn something. And I will show you some solutions to problems, but these will not be the best solution possible. So if we are in applied research, so if we have a working solution that's good enough, then we will stop trying out something new. And so maybe we'll come up with a better solution. But yeah, this is not what applied research is about, just a little disclaimer. So a few sentences about myself. Some of you I already met in the networking session. I studied computer science and media, and since over 4 years, I'm in applied research as data scientist, research assistant for machine learning in the renewable energy context. And since this year, I'm also a part-time external PhD student in Marius' team. So I'm trying to give a little bit more time on research and not on applied research, but since this is has to be combined with my daily work, so I don't have as much time, hopefully more next year. Okay, so now some sentences about my institute where I'm working at, since this is quite important to understand what we are doing and what people are working there with which intention to understand the whole story. So I'm working at the Center for Solar Energy and Hydrogen Research Baden-Württemberg. I will just call it ZSW because that's the German abbreviation for it. And we are a non-profit foundation. If you know the Fraunhofer Institute, we are just really similar to the Fraunhofer Institute. We're not connected to them, but it works the same way. We have about 350 employees. Most of them are researchers and, of course, some students and scientific assistants. And the goal of our foundation, of the ZSW, is to make some development and research for technology for sustainable and climate-friendly energy, which also means electricity, heat, and fuels. And the focus is especially on technology transfer for the industry. So we cover, we have different locations. Main location is Stuttgart, then Ulm, but we also have some test sites where we can have our own wind test site and solar test site. So a lot of data collected there. And if you ever come to Stuttgart, you can just come by, or we can meet. Or if you're going to the Schwäbische Alb, then you can see the wind test site, from our institute. So to show you again, the topics we are working in at the ZSW, it's wind power and solar power, but also like materials for photovoltaics, batteries and hydrogen, and with hydrogen also fuel cells, and we also do consulting for decision makers. So the ZSW is also often in the German Tagesschau. If you hear something about next, we not a record in how many renewable energies were produced this year, then it's really likely that the ZSW was somehow involved to make these statistics. And machine learning is a core topic since over 25 years, and which we are kind of proud of. So we started quite early, or my colleagues started quite early to use machine learning for the research on renewable energies. This is mainly because we started with optimizing forecasts with weather data, and weather data was one of the first topics that were supported with machine learning, at least in this context. And today, yeah, you can see that. I also have the slides, so you can read that in detail later if you're interested in. And today we are a team of 11 members for the machine learning team in Stuttgart, and we do projects and consulting for industry, and also sometimes purely research projects. And we work a lot in cooperation with the domain experts from the other departments of the ZSW. We have our own cluster, and our key topics are monitoring, forecasting, predictive maintenance, or digital twins, and which are most of the time tabular data and time series data tasks, but sometimes we also do image segmentation, classification. And these are just 2 examples I will not cover today, but yeah. So this is the background, so you can understand now what I will talk about, and I will talk about our long journey towards AutoML. So this is the challenge we were facing many, many years ago, or from the start of the institute. So we have a lot of domain experts, really with high expertise. So these are researchers, they do cutting edge research worldwide. We have in some fields, we're really doing high level, high class research, and so really experts from all over Europe, electrochemists, process engineers, material scientists, etc. As I already mentioned, we have quite different topics. So these experts, they do have problems that can be solved with machine learning. And also, often they also have a lot of data, and they know a lot of their data. They collect these data, they're the expert on their data. But they have limited or no knowledge of machine learning. And the first step is, of course, that we as a machine learning team give them some information, get in contact with them and tell them something about machine learning. That's the prerequisite, of course. But even if we say, hey, okay, that sounds good, and we understand the core problem, it's not so easy to tackle this challenge, since, it's the first approach which we tried many years. I called it lost in communication. It failed. Spoiler. So the idea was, and I think this approach many institutes are going, and but I can't imagine it's working really well, is, okay, the domain expert, they talk to the machine learning expert, and they just give them their data, and the machine learning expert develops and optimizes a machine learning model based on the data and based on what the machine learning expert thinks the problem is, and then the domain expert receives the final model and maybe with some code around it and can address their problem. But this is not really working, as I already told, since it also already starts with the data pre-processing. So the data the domain experts will give to the machine learning expert is not ML ready. And to do that, it's really often the case that you need some deeper knowledge about the data. So we don't have like easy understandable data like product data or I don't know, images. Most of the time we have tabular data and you don't even know what the column means. So you have to make a lot of communication as a machine learning expert with the domain expert to understand what column means what and what is a good test set, what is represented for the test set, etc. And even if you have machine learning ready data, then maybe you can train some model on it, but to understand the results is also like really domain specific. So we had some cases where we thought, okay, this is like a really bad performing model. And the domain expert is like, oh, 30% error, that's perfect. So it really depends on the domain, and also in this step, a lot of communication is required. And even if you have made to build a model, train a model, it's always the case that the domain expert wants to change something or they want to integrate it. And especially they want to write some paper about what they did. And then they have to communicate again with the machine learning expert and they don't understand what the expert was doing, etc. So you can see a lot of communication is required, which is not only time consuming, but also really prone to misunderstandings. So we had some years ago, I think like 7 years ago, a better idea: empower the domain experts with low-code AutoML. So what we did is build some Jupyter notebook with some code snippets and some explanations and instructions. Oh, sorry, here's a typo. And yeah, tell them just like what they have to change if they have to change it, where they have to execute the code, and trying to run so the domain expert is running the notebook and we are just supporting him. And the underlying code is automating as much as possible. I think sometimes you cannot call it AutoML since it's too simple or something, just some logical rules, but sometimes it's really AutoML methods behind it. And the machine learning expert, they only serve in a supporting role. So I have found some video online where, okay, so so where my colleague is making some tutorial about how to use this notebook. As I said, it's low code with a lot of explanation. So, and this was like 7 years ago, and as you might think, the problem about this, so it worked for some people, but only those domain experts with a Python coding background. And at least in our institute, most of the people, they don't code at all, or they don't use Python. They all of them use MATLAB. So this low-code version will not work for them. And so the same is true for all the low-code frameworks we talked about today. It's not working for domain experts. So the final result was a game changer, combining no-code and AutoML. And this was possible with so we made this project, KI Lab EE, EE for erneuerbare Energien, renewable energies, where we built a web tool where you don't need any line of code, and I will show you later how this works. And we were lucky to have some support from different projects from Baden-Württemberg and the Bundesregion. So they supported us in building this no-code platform, not only for the ZSW, but also for other smaller and medium-sized companies. So if you're working in a small and medium-sized company, you can just use this tool for free. And also you can use this tool for free if you're working in renewable energy context. This is also where you can use it for free. So, and what's so good about this platform, or what is it about? It's just an pipeline suite for tabular and time series data, so we don't cover image data, since there also already exist some no-code platforms, open source. And it's a user-friendly interface, has detailed explanations and interactive plots. You have some model export that does not require Python packages. And yeah, from an AutoML perspective, it's not an AutoML system, I would say, but it's like a wrapper, a GUI and a API that wraps on and brings together different AutoML methods or AutoML systems. But you will see it when I show you. And we have some automated preprocessing and automated data science integrated. We have hyperparameter optimization. In this case, we have only the random search and black box optimizer, PGPE. We have automated feature selection. And of course, there are a lot of ideas, which additional AutoML methods we can use. And I already came up with some today, so a lot of plans. So reasons for the domain expert to use such a no-code tool is to be able to access machine learning without deeper prior machine learning knowledge. Yeah, since everything is automated and validated wherever possible. Then maybe, okay, not for all of you important, but we have German language support, which is for a lot of people really important, since the descriptions or the machine learning is always in English and all the websites. And so if they just addressed in the right language and not only the language, but only the simplicity, yeah, they feel, yeah, it's much more easier for them to use. And yeah, we also integrated some beginner-friendly explanations and have an emphasis on explainability. But there are also reasons for machine learning experts to use a no-code tool. I think if you can save time and don't have to code everything, and everything is automated and validated, it's also quite handy for machine learning experts. We integrated some advanced option to configure also for advanced users. And of course, the interactive plots are also a reason for machine learning experts. And everything is tracked in the background with ML flow, which gives you a nice tracking overview, even for the experts. So, and now I will show you. So I will show you now our new version of the tool. It's still in beta, but yeah, and I will tell you how to use it at the end of my talk. So, and I will write it also on Discord, how you can use it. And yeah, I hope you can see something. At least I made a text. Written is not so important, but as you can see, it's really clean and simple and a lot of explanations given. So, because people come to the tool and then don't know how to start. So you can either browse some sample data sets we prepared, or not only data set, but machine learning tasks with some difficulty, how difficult this task is to run through. Or you can upload your own data set, and this I will show you. So in this case, I will show quite simple data set, not from renewable energy, but it's about milk quality. It's a cable data set. So we have different measurements, pH and temperature, smell, turbidity, color, etc. And then the resulting milk quality that was that was assessed. And we have some, I think some 100 different milks here, and I will use. So everything that is a CSV data file will work. The only prerequisite is you have at minimum 3 columns and at minimum 20 rows, and at maximum 1 million rows. And you can also use emojis in your data set name. That's really an important feature for the younger generation. So, okay. So, and here we have the first check. So for the user, it's quite a simple check in this case. The column name is quite long, so you notice if you have some plots and the name is too long, it won't look good. So we can change it here, and we say just production site. Save this, and start our data set creation. So, and for each data set, you can configure different experiments. So, and as you can already see, we have 3 different types of experiment. And again, there's a lot of explanation because domain experts, they don't know what a regression and classification task is, maybe, or they have a different understanding what it means. So we have a lot of explanations. If you're a machine learning expert, you know you don't have to read it. You just click Create Experiment. And now it's about just to tell what is your target, or what are your targets, and what are your features. And in this case, we want to use the milk quality as a target, and maybe we will decide that we want to ignore the production side, since in our use case there are only 2 of them. So now, and you can always read some additional information on this of each of these options. So, and now I would say machine learning pipeline supported with AutoML begins. So we do now the pre-processing. So we do some pre-processing, some model agnostic pre-processing, I would say. So since we say, okay, you always have to check for constant columns, you always have to do one-hot encoding, and you always want to normalize your data. Sometimes it's not necessary, but it helps to get some idea of the data set. And in the future, we also want to do some intelligent data imputation. So in this case, we just replace them with -1, and you can also use some intelligent methods here. So automated pre-processing, like machine learning based feature imputation. So, and this is real time. The pre-processing is finished, and now we can see some overview about our data. And this page, it's quite important. I don't have a data set with errors or warnings, but we will give the domain experts some warnings about what's not good about this data set. For example, if the target has not a good distribution that is suitable for machine learning, or there are too many missing values in some features. And so then if you have an error, the experiment, you can't go on. If you have a warning, you can decide to accept the warning and go further, or you can create a new experiment, for example, where you just ignore the feature. And of course, everything here, warnings, it could be really intelligent. Right now it's just some logical implementation, but you can do some unsupervised stuff here. And then you can inspect the data. and you get some plots about your data. And of course, you can already make some nice plotting here. Maybe something like Thomas showed us. You could also already integrate it. And now we come to the real machine learning, and this is how we present our user the options for machine learning. Okay, you can choose some HPO method. As I told you, we only have the PGBE and random search, but here we could all include also AutoScaLearn or AutoGluon, or this is like, so this is why I said it's not an AutoML system. Here you can could implement something else here. And but in this case, we don't want, since the domain expert, they really want to understand what they're doing. So we decided that we want the user to make the decision which kind of model type they use. And we would like to give them as much information about what a model type makes it better than others, since if the more they understand about the process, the more likely they will understand when something is going wrong. Okay, in this case, we can use a neural network. We have number of trainings, and not time limit, but number of trainings. And for simplicity, I will only say 12 different hyperparameter options. And in this case, we can show you some advanced options. So this is the search space. What do you want to optimize? What are the defaults? What is not optimized? And I will just set it so this will be a little bit faster. And then you can start a training pipeline. And it will go on our cluster in Stuttgart now, and the training will start. Yeah. So, and here we have some explanation what is going on, what is automated. So for the domain expert to understand what's happening. And if one training is done, yeah, like that, you can get some plotting about the tested hyperparameters and the score. Oh. Yeah, and once you're finished, you can analyze your run. I will choose, yeah. And then the user will get some plots about their results and with some explanation what it means. Since domain experts, they don't know what a confusion matrix is. And we also included Shapley and some feature important based on it's dependent on the model you're choosing, how it works. And yeah, I think this is enough for a brief overview. I hope you get the impression what this tool is about. So you can also compare different runs. In our first version, which is available here, if you create an account, we also have some additional features, but the GUI is not as nice, and so I always only show you the beta. You can also read something about the idea and how the pricing model is, but I think you got the impression. Okay, and before I start with the second part of my presentation, use cases made together with domain experts. Do you have any questions on the tool?
Yeah, like for example, if I choose some like models or algorithms for classification, for example, scroll back on chain as they are, and we select the data, and we select everything by programming first, like the iteration and provider. And eventually, can I download the whole Python code?
Yeah, sorry. Here is download model. So then you can download the model in Onyx. So it's the trained model. It's not the training code, but the trained model you can download in an Onyx format, and the Python code to use it for predictions, inference.
It's in Python, right?
Yeah, the Onyx is a format that can be transferred in other languages, but yeah, you can read it with Python.
Okay, there you go.
Yeah. Okay, you can also ask me later on the tool. But so I will continue with some real-world machine learning or AutoML examples from the renewable energy context, which were partly made possible with the no-code platform. And it's always an example we did together with the domain experts. And I have two types of examples I want to show you. Type 1 is the classic one, I would say. So the user wants to use machine learning to automate classification and regression tasks. So for a task with recurring data, the user wants to obtain a model they can use in their daily work. This is classic task. And for these kind of examples, we use automated data science, as you've seen in our tool, for example, and HPO to train the model. And first example is example from wind power. So we did predictive maintenance for wind turbines. The problem with some wind turbines, even in Germany, is that they are at risk of icing. So the turbine has some icing, and if it's still running, it gets a lot of significant damage onto the blades and other components. So you want to detect icing as early as possible to shut down the turbines and prevent material damage, and of course reduce some long-term maintenance costs. And predictive maintenance is a typical task for machine learning, as most of you might know. So what we did is we trained and optimized a machine learning model to forecast the future wind power using weather data, weather forecast data, historical measurements, and the previous power output from the wind turbine. And also we use probabilistic forecasts to get some prediction uncertainty. And in practice, then you look at the difference between the measurement of what power is produced and predicted probabilistic forecast. And if there's a significant discrepancy, then the operator will be alerted. And this is one example from the test set. So you can ignore the epsilon axis, since everything is normalized to fit in one plot. But important is the blue line, which is the measured wind power, and the orange line, which is the predicted wind power, and the light blue shapes, they show the certainty of the model. So as you can see here, the measurement differs a lot from the prediction, also is out of the certainty range or unlikely due to the probabilistic forecast. And so we are giving some hours before the production drops a warning that something is not good. And as what you can see here, the pink shape, this is where the wind operator would detect this icing. So this is much earlier, and so classical case of predictive maintenance, made possible in this case with probabilistic forecasts and of course hyperparameter HPO models, optimized models. So second example is quite unusual, I would say. So it's from the battery production at the ZSW. And for batteries, for electromobility, you need this coating and electrode coating. And this is quite a crucial step for the battery performance. But it's quite difficult to measure the quality of this coating. And this is done manually by experts using like high resolution images or microscope images, SEM images, and the expert will just give some evaluation about the quality. And this is quite time-consuming and depends heavily on the expert's judgment. So if you could automate this process, it would be save time and, of course, reduce the reliance on expert inspections. So what we did for this, to solve this problem with machine learning, is we only let the main expert label about 100 coatings based on these SEM images, and then trained an optimized stacked model used for classification. I will show you in the next slide. So the input data are the images, and the target is this subjective quality score of the domain expert. And in practice, this can work, and it could automatically provide the coding quality and can be integrated in the production process without the need of manual inspection. So this is how the model or the architecture look like. You have these different images, and they are combined for some CNNs to one Z code that comes in a final CNN, and this one is predicting the quality. And the quality is a score between 1 and 10, and this is and we got a normalized mean squared error of 3%, which is quite impressive on 100 label data. But so in this case, it was a learnable quality measure. So maybe also something new to you that sometimes it only requires 100 data points. Okay, so I talked about the first type of examples, and now I have some different type. So using machine learning for insight generation. This is quite often the case for our domain experts. They don't need something in production, but they want to get some insight about their problem, about their data. And the idea is to use machine learning to get these insights. And in addition to automated data science and HPO, we use automated feature selection, and I will call it automated feature optimum search. But I think maybe someone else could tell me later. It's all, in the end, it's like HPO, but for features. But we will see. So so the domain expert wants to get some insights. Again, I have some examples from the battery production and the coating. I already told you the coating is quite crucial to get a good battery. And if you're researching for new material compositions for the coating, it's quite time-consuming, since you have to make the whole pipeline. You have to produce a whole battery and have to test it in different stages. until you can say how good this coating was. So you want to minimize the number of experiments needed. And of course, most of you might know this is like, there is like a design of experiments where this problem is addressed to get the best next experiments to know something about the process. But we want to use machine learning for that, or we want to see whether it's possible with machine learning. So what we did is we train and optimize a model to predict the electrochemical capacity, since this is what a good battery is about. If the coating is results in a good capacity, then it's a good coating. The input are the material properties of the coating, and yeah, the target is the capacity in a specific charging mode. Then, after the training, we use the automated feature optimum search. So in the end, we use this model, and then we want to see how should we influence the inputs to get a specific target, or the most maximum target, which of course is an optimization problems. And given that, we have the best inputs, best modified inputs are the future experiments. So this bot, it's just a proof of concept. It's not like revolutionary, but you can see here in the x-axis, we have different samples from these different experiments. They were done without machine learning, and they were used as training data. And we are only interested in the blue triangles. And these are the experiments suggested by our machine learning model, which was trained on this data. And then, yeah, we searched, random search in this case, for the best input modifications, so the best material compositions to get maybe a better experiment. In this case, it was not the best experiments. We had this, I think, over here, but they were performed much better than these ones, and they were done by domain experts. So, and this, I just wanted to show you this use case, since we have some other use cases which I can't show you. So, but this is quite a common question for the domain experts. So they want to use machine learning to get some idea what is a good experiment design. Okay, and so my last example is again a forecasting problem. So in this case, hydropower forecast. Run-of-river hydropower is quite difficult to forecast, since you have a lot of variables that have an influence on the hydropower. So if you have a power plant, for example, in the Alps, then you have a lot of tributaries, so small rivers that are fed into the into the river some kilometers away, or hundreds of kilometers away. And of course, you have the weather, is the snow, how much snow is melting, etc. So it's quite complex to make a good forecast for that. So even the domain expert, they don't know exactly which tributary has an influence, or how much influence on the power production. And I would like to show you this in this picture. So you have some water level measurements, as I said, some 100 kilometers away on different rivers, and then the weather forecast, and they together serve as input for the machine learning model. And the problem we want to solve here is to get an understanding which kind of water level measurements at which time have an influence on the power production tomorrow. So, yeah, in the end, it's feature importance, but quite difficult feature importance. So we used it. We just said, okay, we use every measurement from every timestamp from the last, I think, 4 days as a feature, and then you will come up with over 10,000 features. I think it was 30,000 features. So this is like completely different to the data sets we had in the battery case. And we not only want to have the forecast for the next 6 hours, but also for forecast horizons. So we use different networks for each horizon, since we know that different features have different influence on the horizon. And then we use an automated feature selection that iteratively reduces the features, and we get some insight about which water level measurement is important for which forecast horizon. And my colleagues, they made quite a nice visualization of this. So what you see, and rows are the different networks for the forecast horizons. And these columns are the different measurement stations. But as I already told you, we don't have one timestamp, we have a lot of timestamps. So the number of timestamps is indicated in the size of the square. And we start with everything. So this is like all of the 30,000 features. And iteratively, so what you see is the iteration of the feature selection. Some features are sorted out, and in the end, you will see not only how many timestamps are sorted out, but also how important this feature is. So a big square with red color is a really, really important measurement. And you can see this changes sometimes over the forecast horizon, sometimes not. Some measurements are all for each horizon of timestamp the same. And and if you do this iteration a lot of time, then in the end you will learn something about your problem and which river has an influence at which point for the hydropower. So, okay, and with these different examples, I hope you got some impression how to use machine learning and AutoML. Of course, this is not the most intelligent feature selection we had. This could be improved, and if you have some ideas how this is useful for there's maybe some better ideas for time series data, just let me know. But I hope you got some impression, and maybe I will also give you some takeaway messages from the work with domain experts. So domain experts, they don't have machine learning ready data. So for us, it's really important to think about the whole pipeline. I think Matthias, he had quite a nice image about this pipeline, and we are interested in the whole pipeline since we have to start with the domain expert at the start. And domain experts, they are not interested in the best model, but a working one. So for us, if a framework is scoring, has the best score, it's not as important as if a framework is robust to different data sets or is explainable. And this is also the case for the domain experts.
Yes.
And also the takeaway message is that it's not only about classic regression and classification tasks. The domain expert or sometimes also needs some other automation tasks. And so we're also interested in some research on that. And in general, we already talked about this today, and I can only support this since domain expert, they need human-centered AutoML. They want to be kept in the loop. They want to understand what's going on. So this is my takeaway message for today. And Thanks for listening.